It's my pleasure this week to introduce Peter Koroteev. So Peter did his PhD at Minnesota, right, Peter?
Yeah.
Then he moved on as a postdoctoral fellow at Perimeter Institute, where I was as well. That's where I met Peter. And afterwards, he went to UC Davis as a postdoc. And now Peter is in the math department at UC Berkeley, where he's a lecturer. And so that's interesting. He's doing some cutting edge math and physics there. And Peter is an expert in quantum field theories, gauge theories, string theory, especially integrable systems. And today we'll hear more about that. So Bethe Ansatz and Q deformations thereof, and its connections to some pretty rich modern mathematics. So thanks again, Peter, for accepting, and the floor is yours.
Thank you very much, William. Hi, let's begin. So I have, so this is the story about interaction between different fields in mathematics, as William mentioned. So a little bit of algebraic geometry, a little bit of representation theory, quantum field theory. But I do want to start very easy. So if you have any questions, just ask me at any time. So my goal is to make sure that all of you understand what these three parts of the title are: QOpers, QQsystems, and Bethe Ansatz, and how they interact with each other, and why we should consider them together. So why is it very natural to consider them together? So I've been working on this for several years now. So my most frequent collaborators are Anton Seitlin over here, Edward Frankel, and Daniel Sage. So Dan and Anton are at LSU, Louisiana State University, so the faculty members, and Ed Frankel is a faculty member at UC Berkeley. And then here are the list of papers. You can it kind of starts around 2017, kind of at least mathematical part of our project, and then we go on for towards developing a more universal picture, which would be understanding this interaction between quantum and classical integrable systems, which in a sense, which is actually part of a bigger story, which is the quantum geometric Langlands correspondence. So if you like kind of familiar with Langlands, I hope you'll enjoy this presentation here. So here, let me just mention some points and motivation. So yeah, it's a very so no matter where you start from, you can always arrive to this topic. So we have first one is quantum geometry and integrable systems, and then when you say quantum geometry, it's most like so foremost it's quantum K-theory and quantum cosmology of some spaces, which people studied a lot in the context of Gromov-Wheatley invariants, and then gauge linear sigma models. So it started with the the notion of homological mirror symmetry and how I can explain it using physics. But then the subject became more and more mathematically solid, and then in particular the part of the story that is relevant to my talk is originated from works by Andrei Oppenkoff and et al. And then my collaborators and I, we did some follow-up work there. But I'm not going to talk about this today. So I'm not going to do any quantum K-theory, although like you can formulate everything I say on using this language. Then more from the physics point of view, there is this program which is called BPS-CFT correspondence, which is essentially it's a duality between two types of systems. One is the supersymmetric gauge theory, and the other one is the conformal field theory. And CFT should be understood in a very broad sense. So it's you should think of you can replace CFT with a construction of a vertex operator algebra or some quantum vertex deformed vertex operator algebra, and then using counting of BPS invariants, you can actually build this VOA or QVOA from scratch, right? And Sort of a sort of most typical example is the AGT aldehyde iota to Chicaba correspondence. Well, then there's geometrical Langlands, and then what's relevant for my story is the quantum deformation, the q-Langlands, where the d modules are replaced by difference d modules. So everything wherever we had differential operators or opers, what it matters now get difference operators or differential or q-Opers. So Q stands for quantum difference operator for Q deformation. It's the same Q is in quantum groups. And finally, this story that I've been interested in recently, the ODIM correspondence. This is well, it's a long topic by now. So it started with works of BLZ, Bajanov, Lukianov, and Lochikov. So they found that if you study a spectrum of, well, if you study the system of the quantum KdV Koroteev-de Vries differential equations, so that's the ODE side, and you study the singular behavior of its solutions, then coefficients in the expansion of those solutions around x equals 0. So those coefficients are not just arbitrary functions, there are some entire functions of the energy of the particle which the system is describing, and then they satisfy the QQ system. Right? So it's very similar QQ system that I will present to you today, although with a slightly different boundary condition. So yeah, so that's where the motivation goes. So if you want to comment on any of these or during the talk or now, you're welcome. You're welcome to do so. I hope at least one of these 4 topics is close to your interest. Okay. So now I want to talk about 2 types of integrable models today and how they interact with each other. So the first type is the integrable or exactly solvable many-body systems. And of course, the most famous one, or at least I think the most famous one, is the Calogero-Moser system. So Calogero, so here's Francesco Calogero. In 1971, he introduced a new integrable system. It was new at the time. And Moser in 1975 proved that it's integrable using lax pairs. So the Lax's work was somewhere between. So Calogero didn't know it, and then Moser and then Sutherland also completed some proofs. So this is the Hamiltonian. So think of n particles either on a line or on a circle with periodic boundary conditions. And this is the Hamiltonian for the system. So kinetic term, so assuming all masses are the same, and the pairwise interaction. So every particle interacts with every other. So xi's and xj's are the positions of those particles, and g is the coupling constant. Now, the way it's written here, this is called rational Calogero because the potential is the rational function, and it describes particles on a line, right? So to get the periodic boundary conditions, the potential will become more complicated. So the system admits generalizations. So the formula that I wrote for you is called rational Calogero. So whose potential is roughly 1 over z. So as you'll see later, we're not going to just look at the So here P and X I assume to be real, right? Because it's coordinate and momentum. But we will want to complexify it later, right? So yes, like a canonical degree of freedom, the coordinate and the conjugate momentum will have 4 real degrees of freedom or 2 complex. So we'll have some algebraic complex integrable system. But anyhow, so rational Calogero system generalized to trigonometric when the potential is either, well, depending on your kind of boundary conditions, you can do either sinh or sine, but just you add 1 periodic direction, or you can have elliptic Calogero system when the potential is the Weierstrass pay function, right? And the elliptic parameter of the pay function is related to the radius of the circle on which you compactify all your particles. Okay, so far so good. Any questions here? It's just interrupt me at any time. Okay, and then another family of generalizations was proposed by Simon Rosenars. So he's still actually working in the field. Yeah. So, and then there's also co-authored by Schneider. So these, there's also a family of RS models, rational, trigonometric, and elliptic, right? And physically, it means that we consider relativistic generalization, right? So it's Hamiltonians are manifestly relativistic. So in some gauge, you have square roots with appears in Einstein theory. But if you like, you can gauge it away. So there are no square roots. But what will be important for us is all the coordinates will now take values in C star in the complex in the multiplicative group of complex numbers, meaning that it's sort of instead of coordinate z, we'll have something like exponential to some epsilon epsilon z, where epsilon is some dimensional full parameter, which has the sort of if you like, it's something like 1/c. 1/c is the speed of light. So the Calogero system is reproduced by taking the limit. So you take the RS Hamiltonian. I'll write it in several slides later, and subtract n times the mc squared, right? So times the rest energy, and then take speed of light to infinity. You'll get the relativistic limit. Excuse me, non-relativistic limit. And finally, a bit later, after all this, people did their work. Mathematicians, algebraic geometers came in, and then they formulated these integrable systems in a very rigorous manner using Hamiltonian reduction of the so TRS, for example, the Hamiltonian reduction of the cotangent bundle to JLN, right? Sort of, yeah, sort of, and then there's a whole geometric story about it. I'm not going to describe it today, but yeah, so it's like it's a story for another talk. Questions? Okay, so I assume that then it's all familiar. Right, now, where else can you generalize it? Well, so we can put things on the table, right? So here I call it the I-type table. So the reason for it is because the Calogero himself, when he was developing Calogero model, he spent part of the time in ITAP in Moscow. So yeah, he was a frequent visitor. And then people there, they contributed a lot in developing all these theories. So in my recent paper with Gorsky, Alicia, and Shamil Shakirov, we just summarize a lot of progress here. So if you look at the rows in the table, they denote the dependence on the Hamiltonians on the coordinates, right? So rational, trigonometric, and elliptic, and then excuse me, on momenta, and then the columns will show you dependence on the coordinates. So again, you have rational, trigonometric, and elliptic, and as you can guess, there are nine possible combinations, right? So there's nothing beyond elliptic, as we know. There's a group theory reason for that, right? So, and then, yeah, otherwise we have all possible combinations, rational, trigonometric, and so on and so forth. And then, as you can see, only the upper part kind of makes sense, because the rest you can just define by doing the Fourier transform, right? Just by exchanging x and p. So there's elliptic Calogero-Moser-Sutherland, there's elliptic RS, and then in the top of this hierarchy, there's this very interesting and sophisticated model, which we call DEL, right? And the joke that DEL is not a computer, right? DEL stands for double elliptic, right? So it's a model with the coordinate and moment are they both live on an elliptic curve, right? And the phase space will be certain kind of symmetric product of it's actually not a product, it's an abelian surface, but at least for 1 degree of freedom, when you have one elliptic curve fibered over another elliptic curve. Yeah. So the fibration is non-trivial. Yeah. So in my story today, we'll focus on this guy in the middle, one of my absolutely favorite models, trigonometric RS system. Yeah, so that will be kind of one part of the correspondence where the QOpers will live. And next, I want to remind you about the Bethe Ansatz, right? So I promised to explain every word and title. So I thought it might be a good idea to remind you guys the coordinate Bethe Ansatz, because I want to show explicit formula for Bethe equations, which are probably based on the list of the participants don't need to do. But anyhow, so if you like, I can go really fast over this. So do you guys want me to go over Bethe Ansatz, or shall I just show you this slide?
Best to be explicit.
Say again, please.
Yes, you can go at a decent speed, but you can go through it.
Yeah, okay, sure. Yeah. Okay, good, sure. Great.
Don't want to lose the audience, be explicit. Define.
Yeah. Right, so this is the famous Heisenberg XXX spin chain. And this is the Hamiltonian for it. So you have spins up and down, right? It's manifestly SU2 symmetric, and SU2 algebra interchanges spin up and spin down. So there's a raising operator, lowering operator, and the Cartan, right? So spin up has eigenvalue +1, spin down has eigenvalue -1, and so on. So you have, you can write this Hamiltonian like have a spin chain, like there's a state with the spins up and down, right? And the Hamiltonian is the sum of the pairwise interactions, so which kind of make the spins talk to each other, right? And you can formulate it in many different ways. One of them is that it's a, if you have two spins, then the action of the Hamiltonian up to a common factor boils down to identity operator, well, that does nothing, minus the permutation, right? So for example, if you have spin up, spin down, the Hamiltonian, so it maps it to spin down, spin up. Sorry, identity, excuse me, that's the permutation part, but it will give you the, now let me start over. So it would take, if you take spin up, spin down, it will map it to spin up, spin down, minus spin down, spin up, right? And if we have, for example, up, up, right, then it's 0. So the sort of natural question is to diagonalize this Hamiltonian. So say you have some number of spins. So find the set of eigenvalues and eigenvectors. First, like now with powerful computers, you can just put it in the Mathematica and then ask it to do it. But like it's actually getting pretty cumbersome very quickly. So for example, for 20 spins, the basis has about 10,000 elements. So it's not a very powerful, not very nice way to do it. So that's what Bethe came up with. So we'll classify the eigenstates based on the filling level, right? So the vacuum here has all spins down. Again, it's a choice. This is a so-called ferromagnetic vacuum, and existence of a ferromagnetic vacuum is connected to the overall sign here. So I think with the choice of the plus sign, you have a ferromagnetic vacuum. So all spins down. So as we discussed, Hamiltonian acting on down, down gives you 0. So it's actually a vacuum, it has 0 energy, right? And then sort of on the next level, we have one of the spins flipped up at position K. So we call this state cat K, okay? And all the others are down. Okay, so let's try to compute its eigenvalue. So to do this, we'll make a discrete Fourier transform, and here we can assume that the chain is actually infinite, right? So we have, well, it's like very long. So we take sum over k, right? So all positions of those flip times the plane wave times e to the ipk. Okay, and then if you act on this state cat p with the Hamiltonian that I showed you in the previous slide, you can see that every contribution will be trivial except the one which sort of borders with the flip. Right, and we have this contribution. We have 4 terms which are non-trivial, which you can, after shifts, because it's an infinite state, you can package them into the 1 minus cosine p. So that's first level, and then now we need to see what happens when I have 2 excitations, right? So the 2 excitation level, we have spin up at position k, spin up at position l. Again, we make a Fourier transform, assuming that they are ordered like this, so it's e to the ipk plus iql, and we call this state p cat p less q. And then we can see that this is almost an eigenfunction. So Hamiltonian exponent state P less Q is equal to E of P plus E of Q. So these are the dispersion relations from the previous page, 1 plus cosine, but this contact term, right? So like there's these two spins which are next to each other that prevent the state from being an eigenstate. So you can do it for P less Q, you can do it for Q less P, have similar looking expressions, right? And then you can just cook up a combination, which is actually an eigenstate if you adjust the coefficients right. So like adding these two states with a coefficient with a function S, which is called the scattering phase, or in more generally for higher ranks, it will be a scattering matrix, which is this rational function of the exponents of P and Q, right? And now this is an eigenstate, and we see that the energy factorizes, right? So the total energy of sort of two-state, two flips is the sum of the first one plus sum of the second one. So there's no correspondence. Okay. And then finally, we need to talk about scattering. So if we have three states, right? Three spins are flipped, right? So then we have 3 factorial asymptotic regions. We can have 1, 2, 3, 1, 3, 2, and so on. And then you can show that this vector will be the eigenstate, right? So, and then kind of the nature of integrability, the integrability manifests itself by saying that this triple scattering process, when we have 1, 2, like the, you should write like this, it's something like S1, 2, 3, right? So the scattering of, so if you want to swap around all three of them, then the factorization process, so that the scattering phase factorizes right into the product of three phases like that. And eigenvalue is the sum of the energies. Okay, and then you can keep going. You can construct all the other states with the other number of flips. Okay, and finally, in order to write down some closed equation for those, so we just what we did so far, we just parameterized the eigenvalues and eigenfunctions using this complex variables P1, P2, and P3. But we need to find equations which would tell us what those guys are, right? Because we haven't solved the problem yet. So this brings us to we now need to impose periodic boundary conditions, right? So we need to have your spins. They go up, down, blah, blah, blah. And then we're assuming that the kind of all the excitation or interest in excitation happens in some compact, in some finitely supported region, right? So those excitations don't go far away to infinity. And then we can sort of close it up, on the back, right? Together, so like spins would live on the circle, right? Potentially a very large circle with periodic boundary conditions. We'll talk about what happens when we twist those conditions. But for now, let's assume that we just make periodic boundary conditions here. And then sort of the Bethe equations comes from the condition that you can take one spin, and you can scatter it around all other spins, and then put it back. And then you would come it back. So from one side, you'll gain this translation factor, like e to the IPL, where L is the total number of sites. So you have translated your wave function, your state around the circle and put it back, right? And then on the other side, it is equal to the product of all the scattering factors, right? S12, S13, S2, S14, etc., S1, L. And then those two things have to be equal to each other, right? So, and this is what the Bethe Ansatz equation tells you. And so you can either write it like this in terms of those P's. They're also called quasi-momenta, right? Quasi because they're periodic, but sort of more conveniently is if we switch to the so-called rapidity description, right? So then if you sort of do this inverse trigonometric transform, then you can write Bethe equation as the rational equation for the rational functions. And then the total energy of every state will be just again the energy factorizes, and the total momentum it has this also complex expression in terms of rapidities. Any questions on the steps? So that's Bethe Ansatz, at least the flavor of it. Now, we do need to introduce some more data to it. So it's not going to be good enough for us. So we'll get two more ingredients. So first, as I mentioned, we can close up the chain with a twisted boundary condition. So we can introduce a, so this is an SC2 example, but so here there will be one twist parameter Z. So there'll be as many twist parameters as the rank, right, as the dimension of the Cartan subalgebra. So you can start a spin chain for every Lie group, the Lie algebra. Right. So on one side we have twist parameter, and also one more thing you can do is you can deform the scattering factor. So we're free to change the magnitude of the interaction between any two neighboring spins. So for example, like in real material, right? So those of you who are in condensed matter background, like William, right, you know that there's disorder, right, in real systems, and then those spins can be at different distances from each other, right? So spins that are further apart, they would interact weaker. Spins that are closer to each other, they will interact stronger, and that will introduce the anisotropy in the interaction. And we take this into account by introducing a set of parameters, right, for every. I think they should be here. They should be in this factor. By introducing the anisotropy parameter for every site of the spin chain. Yeah, and that will be important later. So remarkably, integrability still persists, even including those in the presence of those anisotropies. Okay, so far so good. Right. Now here's the kind of the main statement based on what I just told you. Well, at least kind of the version of the main statement. So there is a duality between quantum systems and classical systems. We call it a quantum classical duality, right? And so I'm just going to give you a particular example of this duality, and we'll kind of I'll prove it to you using different geometric methods. I'll prove it to you from geometric language, but let me just formulate this purely in terms of integrable systems without any notion of any kind of fancy mathematics. So on one side we have quantum spin chain, and for this example I take SUN XXZ spin chain. So XXZ is a certain deformation of XXX when there's an the Hamiltonian looks slightly different, but not much. So there's extra parameter which you can deform it with. So on n sites, so here this n and that n are equal, but it just by accident. So that don't pay too much attention for this for it, although it will kind of be important later. But anyhow, so and in the presence of anisotropies and twisted periodic boundary conditions. And on the right side, on the classical side, we will have the n-particle trigonometric RS model. So I promised you to try the Hamiltonian. So this is the first one. So we have because it's an integrable system, there are n integrals of motion, right, which are in involution. So the Poisson brackets are trivial between all of them. So I wrote commutator, but actually meant Poisson brackets. And then because kind of this variables that they take values in the group, should actually think like the symplectic form. It's not just some dp dx, it's rather d log p d log x or d log z, some or all directions. And here's an example of the first Hamiltonian. So this is a relativistic system. Every variable here is an exponential, so it's and then if you send speed of light to 0 to infinity, you'll get a Calogero Hamiltonian that I showed you before. Yeah, with a sign function. So what does the duality say? The duality says that the energy level equations for these Hamiltonians are in one-to-one correspondence with the with the space of solutions, right, of the Bethe Ansatz equations for this spin chain, right? And so the way the duality works is that the twist eigenvalues on the spin chain are identified with the coordinates on the integrable system. And the equivariant parameters are identified with the anisotropies, geometrically they call equivariant parameters. Okay, I promise not to use any fancy language, but here it is. It comes from global symmetry. Anyhow, so let me just call them equivariant parameters, which are the anisotropies on all the interactions between spins, and they map to some symmetric functions. So the energies of the energies of the energy levels of those TRS Hamiltonians are certain symmetric functions of those anisotropy parameters. So to put it differently, if you take a spin chain and you look at all possible twist boundary conditions, right, and the anisotropy parameters between spins. So what it does for you, it provides you a phase space for a new integrable system, which is in this case is a TRS. So the classical integrable system lives on the parameter space of the quantum spin chain. Okay. So yeah, that's right. So that's sort of one of the ways to formulate the statement. Yep. So we're not looking at the kind of solution spectrum of a particular integrable systems here and particular integrable systems there. It's more like a sort of a correspondence between parameter spaces. Okay, good. So right, so that's this is the dictionary, and then so there's also hierarchy. You can the similar correspondence works for different types of models. So the sort of on a spin chain level, there's a similar kind of diamond. You can take some limits, right? So from XZ chain, you can get to XXX chain, and then by other sort of network of dualities, you can get to what is known as trigonometric Gadan model, and then from there you get to rational Gadan model, and it has something to do with where your coordinates and momenta live. So if they both live in C star, right, if they're non-zero, then it's trigonometric. So you have TRS model and XXZ chain, and then if you sort of blow down some circles, then you'll get some degenerations, right? So the XXX chain is one of the degenerations, and Gadan is further degeneration, and so on and so forth. Okay, good. So right, and then so like this kind of dualities were found by either in physics literature or by people from integrable systems world, but it definitely it sort of asks for a more sort of geometric, more systematic way to way to explain it, and then can you generalize it even further, right? So can you kind of get a sort of bigger, kind of more formal picture, so to say, so that this correspondence will be very natural. Okay. So I'm going to switch gears now. We'll talk about q-Opers. So okay, I explained you so far only one part of the title, so the Bethe Ansatz. Now there'll be the two other parts, the q-Opers and the QQsystem will be, so q-Opers will go sort of generalization of the classical side, and the QQsystem will be generalization of the quantum side. And I'll show you that kind of there is a duality, or rather there's like a three-way correspondence between the three things. Okay, so good. Now let's start fresh. Let's see if we can understand this geometrically. So consider a vector bundle of a CP1, and then consider the map M sub q from P1 to itself, which just multiplies the coordinate by a non-zero number q. Right? So that induces map of, then you have map of vector bundles A from E to EQ, where EQ is the pullback of the bundle by this map MQ. And sort of the bundles go in a different direction. And then upon choice of some trivialization, this map, right, will be it will take values in JLN, C of Z, so it will be functions of Z, sort of inside matrices, inside n by n matrices which are invertible. And then if you decide to change the trivialization on P1, then this map will change. You can easily check that by, so if g of z is the function that changes the trivialization, some holomorphic function, or maybe potentially meromorphic, then this map changes like this, right? And if you can, I hope you can see that this is a generalization of the gauge transformations to the difference world, right? So it's called Q gauge. So if you take, you can, to get the null formula, you can sort of Taylor expand Q around 1, and then you need to sort of formally Taylor expand A around also around 1. And then you'll get 2 terms. Okay, and then kind of you can naturally, so for every linear map A, you can associate a difference equation, which looks like this: the dq of S is equal to AS, where S is the section of this vector bundle. Okay, so here's our first definition. It's taken from the paper, so it's I can show you later which paper it's taken from. So we take the meromorphic GL n, Q connection over P1. So it's a pair, right? We have a vector bundle and the connection where E is trivializable, vector bundle of rank n. If you want to talk about GLN, and A is the meromorphic section of this sheaf, right? So it's home of a structure sheaf over P1 from E to EQ. So basically, it's the way to say everything that I said above, right? Where A is an invertible matrix, right? And if you want to have a unit determinant, then you're talking about SLN FAT connections. Okay, so Q connection is the bundle and this linear map. Now, next, to get an oper, the QOper, we need to add a sub-bundle and an oper condition. So and then for this, let me focus on GL2. So just have rank 2 vector bundle. So GL2, Q oper on P1, it's a triple, right? So it's a bundle. The connection, it's a Q connection, E, A, and L, which is the line sub-bundle of E. And the oper condition tells you that the induced map from L to E mod LQ, right? Because we have, you need to take the pullback, is an isomorphism, right? So the sub bundle is isomorphic to factor bundle taken with a Q grading. So this is called SL2 oper, and if it's called SL2 oper if E, A is an SL2 connection. Now, what does it mean in practice? How can we make it how can we can write any formula with it? Okay, so see what's going on here. Let's take SOZ, which is the section of line bundle L. Okay, and then we can do 2 things with it. So we can either compute S of QZ, right? We can act on the coordinates on P1. We can act on with this map M sub Q, which kind of comes, which you can think of it as a Q monodermy, right? So in fact, if you remove 0 and infinity from the sphere, you'll have a cylinder, right? And then multiplying Z by Q, it's like taking a Q monodermy around the cylinder. So once you take this monodermy, so S of QZ, and then another thing, you can act on this with this linear matrix A of Z. And then the fact that this is, and the fact that here this map is an isomorphism can be written like so. So like these 2 vectors are linearly independent, right? So you take a vector, you rotate it with the linear transformation, right? You can act with A of Z, maybe stretch it, and then it's not parallel, right? It's not parallel to S of QZ. So that's the oper condition. Okay, now actually I have this picture here. So and now we can actually allow this isomorphism to fail at some number of points. And this is where the oper singularities come in. So we say that we have an SL2 q-Oper with the regular singularities at Z1 through Z sub L. And then assuming that none of those 2 points is 0 infinity. With weights, so there's also data, we can associate an integer weight for every singularity. So then we say that this is a q-Oper, a meromorphic q-Oper for which this map, a bar, is an isomorphism everywhere except those points. And then not just those points, but also points that differ by each z, by multiplication by q to the negative, well, 1, -2, -3, up to the corresponding k. So in other words, for every singularity, we have a tower of other singularities which differ from them by the q monodrome. Okay? So if you like those cases, the generalizations of spins, like the spins in Gadan model, if you're familiar with Gadan model. Now, the reason why it's L here and then I had L sites on a spin chain is not accidental, so it will be connected. Okay, and then finally, so yeah, so going a bit further ahead, so these guys will be so these singularities of the oper will correspond to the anisotropies in the spin chain, and the twist parameters in the spin chain will come from the z-twisted condition of the q-Oper. So we say it's another definition. So we say that this oper is z-twisted if the q connection matrix is gauge equivalent to a diagonal matrix with two eigenvalues, with one eigenvalue, say z. Okay. Right. Okay. And one more thing that we need to do is to sort of, it's still not enough. We need to introduce what is known as Mura structure. So before we had a q-Oper, which is a triple, and now we need to add another subbundle L hat, which is preserved by the q connection. So if you think of q connection as a matrix, it will have this invariant subspace. It will have 0 below the diagonal, right? So now let's spell it out more specifically. So let's try to describe the space of this Mura opers. So we choose a trivialization on line bundle F. So let's say S of Z is parameterized by two polynomials. I call them q plus and q minus. And then the twist element, that the central element in SL2, in SL2, right, is the diagonal matrix with eigenvalues zeta and zeta inverse. Now, the q-Oper condition from the previous slide, this one, right? We can specify now. Okay, so now remember, so this condition says that this is always a bar is always an isomorphism. But now we want to allow this isomorphism to fail. So the left-hand side is allowed to vanish at those points, right? It's allowed to vanish at singularities of the oper, and also on the tower of those points, which are obtained by going around the cylinder, right? And then the left-hand side, you can see it's a q-Wronskian, right? If you calculate this determinant, zeta inverse, q plus of z, q minus of z. So it's a 2x2 matrix, q plus of qz, q minus of qz. Right, you calculate the determinant of this 2x2 matrix, you'll get the left-hand side. Okay. Any questions here? Please ask question. Like it's, I'm trying to do it. Okay, okay, maybe. And then and now how to get. So yeah, so this is called the QQ system for SL2, right? And the sort of if we parameterize. Now let's find explicit parameterization of those polynomials q plus and q minus. So we take actually to get Bethe equations, we only need only q plus or q minus. So in fact, it's related to the choice of this subbundle L hat, which is invariant under A. Now the if W sub k are roots of q plus, then we can do a standard trick in integrable systems literature. So we can take this equation and we can evaluate them on roots of q plus, right? Then this term will vanish. And then we can make a q shift, so inverse q shift, and then evaluate on roots of q plus again. So then this term will vanish. And then we can divide the first equation by the second equation. So if you can check that if you do this, you'll get exactly the you'll get this equation, which is nothing but the Bethe Ansatz equation for XXZ spin chain. Here it's on L sites in a sector with M excitations. Yeah. So this is like the very basic example of the correspondence, right? So for every by using by a q, if I start with a q-Oper, I can construct the QQ system and the Bethe equation. Questions here? William, how much more time do I have for the main part? Like 5 minutes or so?
About 10 minutes.
Okay. No. No, I'm just surprised that nobody's saying anything. Is it just because everybody knows it, or it's yeah, okay. Okay, now let me show you explicitly the Q connection. So remember I told you that there's an invariant subspace. There's a flag subbundle which is invariant under the A, under the action of the under the Q connection. So you can, in this case, you can parameterize A like this. It's an upper diagonal matrix with the singularities. So lambda of Z is the polynomial that has singularities of the oper in the upper right corner. Now the Z twisted condition here, you can spell it like this, where V of Z, it's not just any element of the loop group, right? Of SL2, well, of Z, right? But only that only from the Borel subgroup, right, which is preserved by the Q connection, right? So it's a stronger statement, right? It's essentially saying not only can you diagonalize your matrix by some group element, but by an element from a Borel subgroup. So say by the upper diagonal matrix. And then you can work out the algebra and show that this gauge transformation will have this form. Right, there's some polynomial y here, was a rather rational function y, which is related to it should be v. I apologize. So instead of g, it should be v, which is related to v like this, and then the lambda, right? So if you write the condition, the lambda is the singularities of the opers given by this equation, right? And then that leads you to again to the same to the same QQ system. And finally, I mentioned that for every oper, we can construct a Q difference equation, right? So there's a Q shift. We take the components of the section, and one thing you can do is do the Q shift, and the other we can take would act with a Q connection. So because it's a triangular matrix, you can reduce the matrix equation of degree 2 to a scalar equation of difference equation of degree 1. And if you work out the algebra, you can show that the coefficient in front of the first degree shift is the eigenvalue of the transfer matrix of the XXZ chain. Sort of another notion from integrable systems. And here we have data from singularities. Somewhere along the way, you need to assume that these terms do not cancel. It's like the singularities, which are different singularities, they are not q to the integer power away from each other. Because if they are, there will be some cancellations. You can remove some of those singularities away. Okay, good. And then, in which sense does it provide a generalization of this many-body integrable systems, Calogero or TRS? So what the opers have to do with what I just was saying in the beginning? Well, so we can easily recover the two-body TRS Hamiltonians from a simple q-Oper in the following way. So take polynomials q plus and q minus to be the polynomials of degree 1, right? So with some roots, we call them p plus and p minus, and there is some proportionality coefficient c here. And then if you plug them into the oper condition, you'll get a quadratic relation in z, right? And then if you do expand the coefficients, you'll find precisely the two trigonometric RS Hamiltonians in the left-hand side, and on the right-hand side, we have symmetric functions of z plus and z minus. So there will be z plus plus z minus, and z minus times z plus. So you would recover the, in the sense that this integrable system is recovered in very sort of in the, for the simplest possible oper, right? So when those components of the section are polynomials of degree 1. Okay, so that's it for SL2, and maybe I can comment about general case for any group G. Are there any questions about SL2? Okay, so what about any group G? So here G is complex, algebraic, yes, complex, simply connected Lie group, right? And you can define oper for any such group. And it becomes a little bit more formal. So, well, Q connections is the same way. You have some, in this case, you have a principal G bundle, and you have, well, this maps P1 to itself, which maps Z. And then you need to restrict to some Zariski open dense set. Right? So there's Zariski topology in algebraic geometry, right? The closed sets are those which are given by vanishing of polynomial functions. And then you take union intersection of U and the inverse of U under this MQ, and you'll always be working in that set. And then the way you define oper is that so the condition for the isomorphism between subbundle and the factor bundle is replaced by this. So you take the so restriction of the connection on some Zariski open dense set, A from F sub G to F sub GQ on this set, right? It takes value in this double Bruhat cell. So here you take C, which is the product of it's a Coxeter element, right? It's a product of while reflections in G. You take while group of G, you take product of all reflections, and then you sort of sandwich it by these two B minuses, right? So B minus is the negative Borel. So we made some choice for the Borel subalgebra. In this case, it's, well, you make a choice and then you stick with it, right? And then here you made a certain choice of the product of elements in the Coxeter element, product of while reflection. So you demand, your oper condition demands that the Q connection takes values in this Bruhat cell. Okay. So, and locally you can spell it out like this, right? So if so alpha check is the co-root, like the Cartan element, and then n plus and n minus to leave an n minus, right? So unipotent radical, which is the commutant of Borel, B minus with B minus, then A of Z takes this form. So maybe I can show you the formula for A of Z. Maybe I should unskip some slides. Here we go. Just a longer version of this talk I gave at Berkeley. Yeah. So if you take this, you can see the formula in the middle. So you have some, well, yeah. So okay. So anyhow, let me not go ahead too far. Right. So there's that, and then you can well ask yourself, can you well you can define GQ-Oper, you can define Mueller GQ-Oper when you have the second. You have a reduction on the opposite Borel, right? And then you require that these two flags kind of they always take the generic position almost everywhere on P1, and then you can ask, how can you describe the space of this GQ-Opers along the lines we did for SL2 or SLN opers? So it turns out that you cannot do this directly, but you can get help from well, another oper which we call, so let me unskip it here. I was kind of hoping I would be, okay, anyhow. So we take the, it's called Mueller-Plucker oper. So we take the JL2Q or SL2Q. So see, if you have a representation of highest weight, right? With the highest weight, say, omega I, you can act on this vector with the Fi, right? You can act with a lowering operator, And these two vectors will form a subspace. So for every fundamental weight, we'll have a two-dimensional subspace, which is preserved by one of the Borel subgroups, right? And then using this two-dimensional subspace, you can construct an GL2 q-Oper, which acts which is associated to this rank 2 bundle, which comes from this subspace alone, right? And it looks similar to, it looks a bit like what I showed you before for SL2, only that you have this product, and then here AGI is the elements of the Cartan matrix. And then you can similarly formulate the Z-twisted condition for this meromorphic oper, show that it's diagonalizable by an element from the corresponding Borel. So first, you can prove that the space of this meromorphic opers is in one-to-one correspondence with the QQ system, which for any group G takes this form. So the right-hand side now have lambda, which parameterizes singularities of the oper, but also multiplies by this product. And then basically you have, whatever your Dynkin diagram is, say 46, right? So in this, for this node, we have three nodes, so 3 elements in the product, right? And then for this one, we have 2, for this one, you have 1, and so on. So kind of you go over the Dynkin diagram, and then and you take all the products. So that's the first thing you show. And then second, for which I don't have time to anyway, you show that space of all meromorphic opers. So all meromorphic oper is just Mura oper. So the first oper that I have defined is actually you can, in other words, you can chop it by this SL2 pieces one by one, and you can do it consistently by going along the Dynkin diagram so that you will not lose anything. Yeah. So computationally, it's easy to get to QQ system from this two-dimensional SL2 opers. And then in the end, you prove that the every meromorphic oper is also a Mura oper, and that kind of finishes the three-way proof. So you have space duality, correspondence between space of solutions of QQ systems, space of non-degenerate solutions of XXZ equation, which for any group G looks like this. It looks slightly different for non-simple laced groups than for simple laced groups. Some of the terms get squared or cubed, depending on the element of the Cartan matrix. And then you have non-degenerate Z-twisted meromorphic. And then finally, what I just said, from here you can go to just Mura opers. And that proves the equivalence in full generality. Okay, I think I should stop. It's been like almost exactly an hour. But I can talk more if you guys have follow-up questions. I have more slides, yes.
Thanks, Peter. Thanks. It's a nice talk. A lot of material.
Yes, I tried to go easy in the first half, but and then get some results.
But I have questions, but let's see if other members of the audience have questions first. So does anyone have questions for Peter?
Well, I guess I'd like to ask just a very primitive question. It's a pretty big apparatus, but are you basically solving new classes of integrable systems? Is that what are you looking for the eigenvalues?
No. So we don't solve new systems. Rather, we're studying parameter spaces of solutions, right? So as I mentioned in the beginning, so here the let's come here again. So you can play this quantum classical game for pretty much for every group, for every kind of spin chain, any model that you like. So what I'm saying is that so the way the duality works is that, so I don't solve these equations, right? They're complicated polynomial equations. You cannot solve them, unless they're very low degree. And in a sense, we don't need to, right? So what I'm saying is that what space of solutions, whatever it is, right, in other words, there's a better way to describe the space of solutions of the systems of polynomial equations using the energy levels of integrable systems. Okay, so it's like, so think of space of solutions of polynomial equations. Polynomial, because you can multiply by denominators, it's okay. So you don't worry about those poles. Yeah, algebraic geometry, etc. the question, right? So solve the system of algebraic equations. And we're saying, well, you don't need to, right? Essentially, it's not the right question. The right question is that you want to study the space of solutions, and there's a sort of very different way to do it. Either using this, well, integrable systems or the q-Opers. Or to put it differently, you can ask it this way. So you have quantum integrable system. Is there any classical object, like bundle with some sub-bundle, that is completely equivalent to the quantum integrable system? And the answer is yes, this is the q-Oper. Oh, and by the way, I think I forgot to mention that the Planck constant in spin chain, which I sort of conveniently scaled to 1, is always done, corresponds to the coupling constant in the TRS model, right? So here, if you send h to, again, this h is exponential. It's exponential to the actual Planck's constant. So if you, yeah, so right. So the Planck's constant is the coupling in a classical system. And in oper, so that it's the q. So this q, in fact, it's e to the Planck's constant. Does that answer a question, or do you want me to say more on this?
Well, sort of. I guess I'd like to know what the class of models you're looking at is these different variations on Calogier-Moser or Q-Calogier-Moser.
But yeah, it's like that was the motivation. But oper takes you much beyond that, right? So the space of opers is much bigger than phase space of all these Calogier systems.
But which problem are you solving? I understand. I'd like to understand the question and the answer. So what is the question? If it is not the classification of solutions to integrable systems, what is the question?
Well, it's the understanding this duality, right? So dualities are useful, right, in physics and mathematics because they allow you to study questions which are hard on one side and they could be easy on the other side, right? So it's the study of the duality. So we take the equations that we already have. We know integrable systems that we already have. Actually, this is not quite true. So you ask what is the new one. So if you look at this equation here, so Bethe equation for non-simplaced groups. So it was not known before. Like you cannot do the Bethe Ansatz for it. Like you cannot do coordinate Bethe Ansatz for non-simplaced group like that. But our language allows you to formulate it. So it's easy to do we know how to make a q-Oper, for example, for SPN, right? Or G2. For us, there's no problem whether we have a non-simplaced group or simplaced group. And then you can describe the spin chain, the dual spin chain. So it's an example of the story when something hard on one side corresponds to something easy on the other side. Right? Of course, like another example, if you ask William, our host, he will tell you that this ADS-50 correspondence, right? And something is easy on one side is hard on the other side. So it's a question from that sort, right? It's we're studying the landscape of models and how they talk to each other.
Okay, I will have, if there's time, I will have another very...
Okay, sure, yeah.
But I want to leave it over to others.
Okay, so let's see if anyone else wants to intervene. Well, let me ask one question before John continues. This TRS classical system, can you show again the line? So data getter was known from a different context. So the system is, what's the physical meaning of this model?
It's a relativistic. It's the relativistic generalization of trigonometric algebra. So when particles travel fast compared to speed of light. So it's a sort of, you can study, it's a relativistic system. Then you can quantize it. You have relativistic quantum mechanics. We know how to do that as well.
But Relativistic quantum mechanics, you mean quantum field theory, or you mean like the...
No, just relativistic quantum mechanics. Landau-Lifshitz volume 4.
Yeah, but that has all sorts of problems, but you can...
No, I mean, the model itself is fine, right? You can study its quantum spectrum. So quantization works like this, right? You add psi here and ask, is there any, what is it, right? So we have the answer to that as well, geometrically and physically. Okay, so since you ask, so, well, in fact, it's kind of, you can even guess what psi should be, right? So, okay, maybe not guess, but like see how the psi is connected to the other side. So, well, let's take a semi-classical limit, right? Then so we need another, I need another Planck constant here. So h is taken. Maybe let's take little h without the bar, so h divided by 2 pi. So when that thing goes to 0, when this system becomes classical, right? This psi, the wave function behaves as there's a saddle point approximation, right? You have some function here divided by this new Planck's constant h, right, as h goes to 0. And you can ask, what is this w? So it turns out that the w is the potential for these equations. So these equations are what is known as the Jacobian ring for this function. And without taking semi-classical limit, psi itself is a very interesting function. So it counts invariance in quantum K theory of Nakajima Q varieties. And it's what is known as the vertex function of those for the Q varieties. Physically,
sorry, which object counts?
The wave function. So here, yeah, I have a picture with the Q variety. One of the later slides. So what you need to do is the following: is you take, so if you're familiar with this here. So take the space, which is called the cotangent bundle to the complete flag variety. So it's this, well, you should think about it like this, like, you know, there's the Grassmannian, which is the subspaces of k-dimensional hyperplanes in n-dimensional complex space, and you can take a flag. So it's 1-dimensional inside 2-dimensional, 2-dimensional inside 3-dimensional, and so on. And then n-1 dimensional inside n-dimensional. So you have like a chain of embeddings. There's a space, it's called flag. And then you take that, you double it up. You have a cotangent bundle to that flag. So it's a Q variety, which is what Hamiltonian reduction of some space of representations, and there's a whole story. And then it turns out that those generalized Hamiltonians, so they depend on these twist parameters z, there's the zi's and ai's. So in this language, zi's are Kähler parameters for the space. Like every node of the quiver gives you a little sphere, like a little CP1 in the base of the vibration. And then equivariant parameters correspond, these A's are equivariant parameters for the global symmetry. So A1 through AN. So T depends on Z, excuse me, it doesn't depend on, it depends on Z and the conjugate momenta. So if you act on psi, you get elementary symmetric, so T sub I, ith elementary symmetric function of all AIs times psi. So the eigenvalue problem of all TRS operators, so it gives you this. So and psi is known as it's the K theory, quantum equivalent K theory vertex function for that quiver. Well, it's a certain series, it's a formal series in those Kähler parameters whose coefficients are some rational functions, and they will count with some enumerative invariance of that space, or there's some generalization of enumerative invariance. Yeah. So I decided to avoid quantum geometry in this talk because it would, you know, take a lot of time. It's like talk or maybe 2 words and so on. But yeah, so like pretty much every object you have, Hamiltonian wave function has interpretation in physics world, like string theory, and in geometry, quantum geometry, and classical geometry. So it's very remarkable.
Okay, interesting.
Yeah, so so TRS is relativistic interpretation.
I see. Although in this form, maybe it's not
Yes, so like I said, there is a form where there are square roots, right? 1 minus v squared over c squared, but you can get rid of them by redefining the wave functions. Like, it's always nice to work with algebraic, with with rational functions.
You just square the Hamiltonian, but then you lose.
No, it's a bit more subtle than that. You need to twist it. Like it's a little bit more subtle. But you make a similarity transformation that doesn't change the spectrum, but it changes this in a controllable way.
Okay. Okay. All right. Thanks. So, John, did you want to?
Well, I guess I would like just a little more clarification of the meaning of this quantum classical duality. I've seen in integrable systems various versions of interaction between classical and quantum integral systems, mostly in the language of tau functions, which you have not mentioned.
Yes.
I don't know whether that's related in any way to what you're speaking of as quantum classical.
Okay, yeah. So now you need to remind me that the what is it? So there's this. It's about this KP KD. Right. So it's not on top of my head, but I definitely have an idea what that should be. The tau.
Well, I don't want to,
That's okay. So I mean, it's a slightly
both the classical and the quantum interpretation. That in some settings they are partition functions or.
Yeah, I think good. So I think in one setting, right? So in one setting, it's a partition function of some. Okay, so I can give you like the sort of gauge theory answers. In one sense, the tau function is the partition function, the Nekrasov partition function of gauge theory, where you where you specify the Coulomb parameters to some lattice. So basically, it's a partition function of the gauge theory with some restrictions. And there was a paper by, I think, Digraph, Luskovsky. I don't remember on top of my head, but yes, well, you can do it, but at least I don't think it's as manifest as what I'm saying here now. So, so classically, what it's a monodromy, right? Study the monodromy of the KdV equation, right? Can you remind me the classical story?
Well, the classical meaning of the tau function, my understanding, is it's a sort of generating function for all solutions of these hierarchies, like the KP hierarchy.
Like KKP or KdV, yeah, okay.
A sort of generating function in a very classical sense. You can look at it sort of, I like to look at it as something like the Hamilton principal function for a completely integrable system evaluated on the Lagrangian leaves. It's not exactly that, but it's around those, it's that sort of thing. So you have a canonical transformation, etc. And the evaluation of this Hamilton principal function on the
symplectic leaf gives
by the flow parameters they're at least related as logarithmic derivatives with the tau function.
Oh, I see. Good. Sort of. Then it's hopefully will have something to do with this last point here. So this KdV, there's a quantum KdV story here on the ODE side, but then on the IM side, I would still expect some Q functions, some QQsystems, stuff like that. Yeah, I'm sorry, I'm not terribly familiar with that part.
Well, so yeah, just in your context, could you just say what is the classical object that that helps you in some way to understand the solution to the quantum integrable system? What is the connection between what are the objects that enter into this duality?
Well, I mean, I gave you two answers, right? So one of them is the classical integrable system, right? So you have this energy equations, right? So you have the space of energy levels of classical of Hamiltonians of classical integrable system.
But these are the simultaneous. I mean, you've got an integrable system, so you don't have one. You've got
you have to Well, finite. Yeah. So you have n Hamiltonians. You have n equations.
When you say the energy levels, maybe you mean the Lagrangian leaves, Do you mean the invariant? I mean, if you take all of these different invariants, commuting invariants, and look at their simultaneous energy levels, I guess that's the Lagrangian.
Yeah, that's what happens. You take all of them. Yes, you take all of them. So you have n particles, you have n degrees of freedom, and there are n functions which are in involution, right? And you look at all simultaneous energy levels. Yes, that's right. So that would be what it's like the yeah, I guess.
So what role does that play in the quantum system? What does it tell you about the quantum system?
No, I'm saying that the space of like this system of equations is in one-to-one correspondence with a set space of solutions of Bethe Ansatz equations.
Okay, so
Bethe equations, they have these Bethe roots, the rapidities, right? You need to solve for them. So,
but is it the same? Is it the same system? Is it the classical limit of the same system?
No. So, like, for example, in the example, like in the squiver picture, it's kind of clear that no, the counting is completely different. Like say here, for this kind of system, you will have n minus 1 over 2 Bethe roots to have that many Bethe equations, right? And then on the quantum side, you have quadratically many equations, right? And on the quantum side, we'll have just n. We'll have just n theoretic Hamiltonians. So what happens is that you package these unknowns in a very special way, like the TRS momenta, they correspond to certain symmetrized products, ratios of symmetrized products of Bethe roots. And because you have to consider those up to Weil symmetry inside each of those nodes, you actually don't need all of them, but you need to know all the symmetric combinations, right? And if you like this classical system reformulates the quantum problem, sort of like it's already manifestly symmetric. So it's already gauge invariant. Yeah.
So okay, one more stab at trying to understand it. Are you saying that these simultaneous level sets of the energies of one classical system provide you some kind of moduli space for the Bethe Ansatz solutions of the quantum?
Yes, the parameter space. That's right. So you would what the coordinates in the classical system, they would describe your twists, the twisted periodic boundary conditions, and energies are symmetric functions of anisotropy parameters. So the quantum system admits two families of deformations, the twists and anisotropy parameters, which are independent. And I'm saying that these and relations, right, and they form right. So like, I still bit, I'm not sure if we should call it a symplectic leaf because these are not like it's really like okay.
No, I'm not saying the symplectic leaf. It's a Lagrangian leaf. It's a sub, right? It's a Lagrangian formation.
So the sub-variety of one half
dimension.
One half dimension. Yeah. So yeah, I think yeah, I think you're right. I think I can put it this way. So like so those Hamiltonian, yeah, you're doing what's it, type 1 canonical transformation, right? So that your Hamiltonians are formulated in terms of right. So you have this Hamiltonians in terms of the coordinates, so z and pz, right? On those e's are functions of a, right? And then if you have condition like that, right, you don't have canonical. Okay, I think. Okay, let me give you another version of the answers. So here's the full story, which is a bit more subtle. So take the phase space of the integrable system in terms of momenta, so pz and z, okay? But I'm going to do something different. So I want to take a product with its sort of dual copies. So I didn't talk about it, but it turns out that you can also have integrable system where for the anisotropies and for the conjugate momenta to those for A's and PA's, okay? And then there'll be two Lagrangians, right? So there'll be two Lagrangians. One of them, we should preserve the same color. So it'll be, one of them will be Lagrangian, and then the symplectic form will be this. Yeah, I think I'm sure why. Yeah, so take it like omega equals sum dpi, dpi, dzi, dzi, SEI. So this PZ, then plus some dPA, PA, DA, DA, DOA. Okay, so there are two copies of phase space of this integrable classical system, right? So one is this, in one system, these are coordinates, in the other one, A are coordinates, okay? Okay. Good. And now we can have two Lagrangians, one kind of Lagrangian cycle in this form, other Lagrangian cycle in that form, right? So they would, in general, they would intersect transversely, okay? And I claim that those intersections correspond to solutions of beta. Yeah, that's right. So in terms of phase space, it's not enough to have just one phase space. You need to have two phase spaces. So like, because the position of one Lagrangian does not give you the discrete solutions, right? You need to impose some quantization condition, right? And so some condition that would allow you to kind of narrow down to those points.
So that seems like just two different set of independent classical parameters.
Yeah, yeah. Well, I mean, they're not like on the spin chain. They're present at both times. Yeah. So like, yeah. So you have to have like two copies of the Steres model. Yeah.
Okay. But of course, the number of, I mean, the dimension of the space of anisotropy parameters is not necessarily the same.
But so in example that I gave you, would they have a full flag? It is the same. Now you can ask, and it's by design in a sense, right? So it's a very special space. But then you can ask, what happens if it's not the same? And then the answer is that